Okay, let's look at this 1996 extension 2 question on complex numbers. But it's said to be on complex numbers, but the really hard part is on trig, as it's really a common thing in complex numbers. It's a trig algebra question disguised in complex numbers. Sometimes they do add a bit polynomial as well, but really on complex numbers, it's not that hard. 1 and 2, I think it's really easy. You should be able to know it in less than 20 seconds. I don't mean I mean, write it down for like 1 or 2 minutes. So it's a root of unity question. So W is says 2 pi over 9 and show that this is a solution for z to the power of 9 minus 1 equal to 0. So you just plug it in and you use some indices laws to get the result. And the second one, prove this well-known result. It should be easy because after you have this, you can factorize z minus 1 out, which is really, if you've done any question on root of unity, you should be able to do this. You factorize it out, and since it's complex, it's not 0, and then this is 0, you move 1 to the other side. Now the real spice is this part, and since it's an old HSC, there is no mark distribution over here, but I would give 1, maybe 2, and 4 to this question. This is how I would give the marks. So let's look at it. We need to show that the product of three trig values is 1 over 8, a really beautiful simple value. Now, the first method, I tried this method, but I didn't work it out, although it's really the most straightforward way to think of. So we start with this identity, and we want to make a cost. So we think of this way is to divide w to the power 4, because we want to construct this, which we know will give us cost values. So we do that, and we get this result. I think this result is not that hard to get. The real hard to get is how to go from this result to the product of three costs. So what I did wrong is this is a special value, right? Everyone knows that. I got this as special value, and I basically had it as special value, and I have this sum of three trig values. Now I just can't go any further, because three trig value, you can have one product of two trig value plus another trig value, which I can't do anything next. So I should look at this. It teaches you if the method don't work, you go back and try not to evaluate it. That is, you keep it. So let's do this way. We keep it, and then we can use sum to product twice. And the way I chose it is to choose these two and these two. So after you do this, you find out that there is actually a common term, because when you plus them together, these two plus together, these two plus together, they are the same, so they will have one common term. So you get this result, you can factorize it out because they are the same, and then you can basically use sum to product again, and then you have what you want. So it's a very beautiful question, but the beauty doesn't stop there, because the old HSC papers, they have 3 different ways to do it. They include multiple methods, which is way better than nowadays. Of course, it's better than the medieval time when they don't provide sample answers. So the history of HSC is they gave really detailed, I think, sample answers back in the 1990s to the 2005, and then they don't give any sample answer. It's like nothing. Back then they had like in the 1990s, in the sample answer, they would include multiple methods instead of one method. And after some time, I think back in like 2012, they give back the sample answers. So now they just have one answer only, but it's never as good as the 1990s, the golden age. We use conjugate to express cos theta. So this time we basically just start from the result, and we use the conjugate method to express cos, which is really this method to express it. Now we first use this because that's what's gonna appear in the question. Because why do we use this? We want w, right? This you can't write as w. It's not like w. W's argument is 2 pi over 9. You can multiply it by integer. It can be 4 pi over 9, 4 pi over 9, 6 pi over 9, but it can't be 1 pi over 9. So I can use some trig rules to make it a nice 8 pi over 9, which is 4 times 2 pi over 9. Now I can use the conjugate to express it, and then we use some trig rules. This here is because I can plus 2 pi is periodic, and I just brute force it to use the previous result to get the result. Honestly, I really want to share the last method 3, which is honestly very elegant and very, very beautiful solution, although it's kind of hard to think of. So we start from the root of unity, and we just factorize it using factor theorem, which is the result of question 1. We use factor theorem to factorize it. Now, after we factorize it, we can recognize that some of them come in conjugates. So after we do that, we can basically have these sorted out, which are pretty nice and neat, and we can expand them. So z minus k product of z minus k conjugate, we can do some algebra, and we can get this result. So we just plug in k equal to 1, k equals to 2, k equals to 3, k equals to 4, and we get this result. So now, how do you get the result, right? How do you get it? So you already have these, you already have these in the question. You just need to make sure that they're timed together. So you just want to make sure that you can get rid of the z squared term, you can get rid of this, you can get rid of this, then they're actually timed together. You get rid of all of this, then you get the result, right? Also, you need to get rid of this completely. So we plug in z equals to 1 because that makes this disappear. And you'll be happy to find out that you can actually cancel out these terms. So, okay, if you look very carefully here, unfortunately, I made a mistake over here, which is unfortunate. Here, I should all have I here, which I neglected. But since I to the power 4 is 1, so it's not really a harmful mistake, but you can't get marks deducted, you should really add it back here, add it back here, and add it back here. And then you get the result. You can, this is a special value, you can plug it in, and then you get the final result. So this is a very good question, and what it tells you is if you follow the more straightforward method, you reach this step, and you try to make this special value, you stop it in, and you find out you can't do it, go back and try again by using the sum to product twice. This is the take from this video. So a very good video, and through me making these two videos, it's actually good for me because I get to look at it again and find my potential mistakes in the first time. As you see, I didn't see the I there, which I will modify right away. And subscribe for more videos if you enjoy this one.